Okay, let's go through some notes here then. Just so you guys know, I'm going to try to do a couple of demos in my class. I've got a pendulum and a spring kind of set up to kind of do some demos. I'm going to turn the camera towards it. I hope it shows up nicely. So you'll have to give me feedback as to whether that works. So. Okay, here's the two things I want to work on today. We're either going to talk about springs or pendulums. Okay. I won't go to the middle of the room just yet. I'll do that in a second here. But a pendulum going back and forth and back and forth has a frequency and a period to it because it's happening consistently. Okay. Same thing with a spring. Spring's a little trickier. The diagram I have here would be like, imagine a spring is going in and out and in and out. Okay. That's periodic motion. And last day I showed you guys an example of a graph, which we're going to talk about in math for some of you. The graph looks like this, where this would be the pendulum going out and back and out and back. Or I found it better to turn the picture to its side, and hopefully this one makes more sense. Here's the pendulum swinging all the way to one side, all the way back to the other side, all the way back. And this would be like your, I don't know, your distance versus time. Does that make sense? Okay. So those are the types of motions we want to work with. These are not linear or quadratic. We call them periodic. Sometimes we call them sinusoidal. Eventually I want to start talking about circular motion, where something goes in an entire circle. So imagine you weren't just having a pendulum go back and forth. One of the best examples of a pendulum is a child on a swing. If you're like my daughter going on a swing going back and forth, that's a pendulum. If you really pushed her, I would do that to my 2-year-old, but then it would actually be a circle. Does that make sense? So there's a lot of similarities between what we're doing in circles. Okay. Okay, some bolded words I want to talk about here. Everything that undergoes what's called simple harmonic motion, and harmonic motion is basically back and forth motion, okay, has to have what's called a restoring force, which brings something back to what I've bolded as called an equilibrium point. So let me see whether my diagram makes sense here. Here is where this spring happens to be holding a mass. Okay. If I pull this guy out here, if I were to pull it out here, and I were to let go, what would happen? Well, it would fling back this way. Why? Well, because a spring has what's called a restoring force. And often that goes with Fs, is the letter we use for it. I don't know why it's not Fr. Probably because S works better for spring. I don't know. What if you were to compress the spring in? Almost like a trampoline. What if you were to compress a spring in? Well, then it would fling back this way with what's called a restoring force. And the idea would be that it's trying to get it back towards equilibrium. Does that make sense? And try to get back towards its natural spot. So I want to explore these today. Before I do that, though, I need to tell you about a law. It's called Hooke's Law, and this was discovered by Robert Hooke. And probably the best way I can describe it is to imagine you've got a bow and arrow. Or when you were younger, if you had like elastics that you try to like fling at your little sisters. Maybe that's just me. I don't know. Or younger brothers. So imagine you've got elastics that you're trying to fling, or a bow and arrow works too. Okay. Where is the equilibrium position on the bow and arrow? I would say it's probably right there, correct? As I pull back on the drawstring, what happens? Well, there should be more restoring force because the string is going to want to snap back to its original position. If I pull the string back further, there should be more force. Does that make sense? So I've got a diagram up here. It's not particularly large, but displacement and force will have a linear relationship. The further back you pull the string, the more force there would logically be. Does that make sense? Robert Hooke discovered this and eventually managed to figure out a law about this. And here's a formula on your data sheet. To calculate your restoring force, it's equal to negative, I'll talk about the negative in a second, Kx. Okay, so what do these mean? X stands for the expansion or compression distance. So in this example right here, X would be that amount. Does that make sense? Because that's how far back he's pulled it. There's one more factor that matters though. Depends on what your string is made out of. Some strings are very easy to pull back. Other ones, they don't work quite as well. So there has to be a leading coefficient in front. which I've been focusing with, I think, almost all of you guys in math class on, sorry, except for you, on leading coefficients being this number in front that we need to calculate. And so every single, like, spring or pendulum or elastic has its own special leading coefficient that's unique to it. And I think this probably makes sense to you guys. If you were to go grab a bag of elastics, some elastics are very, like, tight, but other ones are very loose and stringy. Does that make sense? And so each one will have, like, their own unique number, and so we need to calculate that number. Okay. And so sometimes I'll have you calculate the elastic constant, so all you're going to do is figure out the force and the distance, or sometimes I'll actually give you that number and ask you to solve something else. So, let's do an example. So suppose I give you a spring, and someone has calculated this leading coefficient value for the spring, so that K value is 18 newtons per meter. Okay. Let's try to figure out how much force the spring can have under these two conditions. So first, let's say you expand the spring by 15 centimeters. So maybe it would help just to draw a quick picture here. Imagine that this spring is, like, there's a wall perhaps, and then the spring is attached to the wall. And normally that's how long the spring is. So this would be like under normal conditions. And then you were to take that spring or elastic band or whatever, and you were to pull that elastic band out by 15 centimeters. So an elastic, a bow and arrow, a spring, anything that's kind of stretchy like that. And so you pull it out 15 centimeters. If you were to pull out 15 centimeters right here, that would be like positive 15 centimeters going that way's positive. Which way is the restoring force going to pull this thing back then? Yeah. And that explains why there's a negative in this formula here. Because if you have a positive distance, the force is going to go back the other way. Now, to be honest, I don't really care about that negative so much, because usually we just care about the actual value of the force. Does that make sense? But that's why this formula comes with that negative, is because whichever way you pull the string, the restoring force is going to try to fling it back the other way. So. Okay, let's use our formula then. Restoring force is equal to negative 18.5 newtons over meters. That's just a leading coefficient that's unique to that particular spring. And then we got to multiply it by our x value, which is 15 centimeters. I can't just times by 15 though. Why don't I just throw 15 in there?
It's not meters.
Yeah, watch your units. It's going to have to be 0.15 meters. Next week we're going to do a lab, and the lab we're going to do is going to be to try to calculate that leading coefficient of K and find the leading coefficient for various springs. Does that make sense? But if you're given that leading coefficient, that K value, then you can actually work with the equation. So, anybody have an answer? What was that? So, well, negative, yeah. Okay, so with sig digs, 2.77 would be negative 2.8. So, I mean, if we were to give this thing a direction, for example, if you were to pull this thing east, then this guy right here is actually going back west. Does that make sense? So, does anything change if you compress the spring instead? And the answer is, well, no, it doesn't actually. If you were to squish in on it, it would fling you back the other way just as much. So the only difference is if you're compressing, let me see if I can redraw this guy now. If you were compressing, if normal was normally here, you've now taken that spring and you've tried to shove everything right into here. And so the distance from where it used to be is now 20 centimeters, but now it's 20 centimeters in. That spring, it's almost like a trampoline maybe, is then going to try to fling you back that way with your restoring force. But the math is no different.
So would it be positive?
Sure, if you were to go with negative 20 centimeters going back that way, then it would just be positive that way. So, to be honest, I don't care about the negative sign. Just make sure you keep it straight in your head as to which way it's going. So, spring force would be equal to your negative 18.5 newtons. You're going to times by negative 0.20 meters, which means it should now be a positive force because it's going to be going that way. that make sense? It's a really easy formula. What'd you guys get? 3.7?
Yeah. Is it going east then, right?
Yeah, I guess if we were saying west was that way, then this one would be going east.
Is it safe to say then that if like your force ends up being a negative, that it'll be going west, but then if it's not negative, going east?
Sure.
As long as you keep out a negative sign.
Sure, that'll work. Yeah. I mean, sometimes I just prefer to ignore all the negatives and then just use common sense and say, okay, well, if I was pushing the spring that way, it's going to restore the spring back this way. Or if I'm pushing the spring this way, then it's going to fling it back the other way. So you just need to keep track of that. Okay. Here's an example that I'd like to actually try to visually do in the classroom. So I'm going to try to turn the camera so you guys can see this. Here's hoping. Hope this works. Okay, what we're going to do here is we're going to attach a mass to a spring on the ceiling, and we're going to see how far the spring stretches, and then we're going to find the spring constant. Okay. So like our goal is to actually find that K value, that leading coefficient. So what I've done here is I've looked at not a spring, but an elastic, which is the same concept. So imagine that this is how far the elastic normally goes. Just check the camera. One of you guys just run the camera and just make sure they can actually see what I'm doing maybe. Because we're looking at their ceiling. You have to look at the little thing in the corner there. Does that look like it's aimed on me?
Yeah.
Okay. Okay, so does this make sense that this would be normally the distance of the elastic slash spring? If I now attach a mass to it, it didn't move by a lot, but it moved by a little bit. And I've got a whole set of masses here, so that we can watch what happens as I add more mass. So this one was 100 grams. So there's your normal distance. There's 200 grams. This would now be 300 grams. Okay. And so does this make sense that as I add more mass, the spring is going to increase in distance? Okay. So imagine that scenario here. Using this, we can now work backwards and find that spring constant. And so let's do this example here now. Hopefully that made sense. I hope you could see that somewhat. Sorry if you couldn't. So let me just draw a picture here to start with. Here's your ceiling. And then here is going to be like your, I'm going to draw a spring just because a spring is easier to kind of draw. Do I care how far the spring normally stretches on its own? The answer is no. Like the elastic was normally however far it was. I don't care what that number is. What I care about is after I put the weight on it, it's obviously going to stretch a further distance with that weight. And so what I care about is the actual like further distance this thing stretches. Does that make sense? So in terms of this picture, this thing went 15.7 centimeters. And this mass right here was 1.5 kilograms. Does that diagram make sense so far? So I don't actually care how big this spring was normally, because it's expandable. Like, it's not a definite number. Heather.
Are we solving for K?
That's our goal. Our goal is going to be to solve for K.
So do you use the like 1.5 kilograms to find the force of gravity?
Ah, good. That's the thing, is that we've got to figure out the free body diagram, and the two forces in play, one of them is the force of gravity. What is preventing this mass from just plummeting to the floor? No? Restoring force. There really isn't a normal force in this example. There's a restoring force. I mean, the spring itself physically is preventing this mass from plummeting to the floor. So the restoring force, come on in, must be the same as the force of gravity. Come on in.
Open the door!
Or not. Thank you. That was a door knock, right? Not crazy?
Well, it's so loud out here.
Oh, sorry. Come on in.
Music.
Anybody else on record?
Is your coffee though?
Always the last choice. It's okay.
I know.
I'm not better.
30 I had 15.
It is.
Well, I've been like, I haven't gotten that really. I'm not yeah.
Okay, so I have some work up here for where you'd go next. Because the spring was not bouncing up and down, because the spring wasn't bouncing up and down, there's no acceleration. If there's no acceleration, then these two things need to be equal to each other. So then make negative kx for the restoring force equal to gravity. Could you close the door again, Lisa? Thank you. Divide by negative x basically to get your k constant. Just be careful on all these negative signs now. Why don't we make this be the positive direction, and let's make this be the negative direction, just so we can keep track of this. Mass will be 1.5 kilograms. Gravity, normally I'd go with negative 9.81. But I said that was in the positive direction, didn't I? So let's go with just 9.81, I guess. And then the distance the spring was going to travel was 15.7 centimeters, so 0.015. Hang on, 0.15.
Yeah.
Sorry. My bad. Usually K values are positive here. I think I'm going to have to throw an extra negative somewhere here. Because we're going to go with negative 0.157 meters. You know what? To be honest, it's probably easier just to ignore the whole negative concept. Does it make sense, though, why the negative is in that formula? Because the force is going the opposite direction. So maybe just ignore that whole negative sign, because just ignore the negative signs. It's simpler. What'd you guys get for a value?
94.
Okay. Does this number mean anything? Not really. Just like any other leading coefficient that we solve for, it's just the value that goes as that a value. Okay. Probably you could say the larger that value, though, like the stiffer the spring, probably. Okay. But really, you can only use it to compare. So 94 newtons per meter is apparently how strong this particular spring was. Does that make sense? So, we're going to do this lab next week, Tuesday, basically. We're going to try to calculate these K values for various different springs and elastics. That make sense? Okay. Okay, let's do some more examples here. Here, I'm going to change the scenario up a little bit. Here, I'm going to throw a mass on a horizontal spring. So rather than having the spring or the elastic go this direction here, I'm going to have the spring go in this direction here. I'd like you to think of my Hot Wheels launcher. I don't know if you guys looked at the launcher all that much, but basically the launcher was a big elastic. And as you press the button, the elastic flings the car forward. Does that make sense? So imagine that on a surface that goes this way here, you've got a spring, so I'm just going to put a wall, and like a spring that goes this way here. And the spring has been stretched out. So normally, this is where normally the spring would go to. But now we've stretched the spring all the way out an extra 12 centimeters. And there's a mass on the end of it. That's 0.250 kilograms. What would happen if I let go?
We go farther back.
Yeah, go back this way. The restoring force would make it move this way. So my question for you is, what's the acceleration? How fast will it be accelerating? Because it's going to start at rest, and it's going to all of a sudden start flinging the other way. So you can imagine how this is useful in, say, like a bow and arrow. I'm going to pull this thing back like this. The question is, how fast will it accelerate? Does that make sense? Heather.
So then when you find your like restore force, that was called?
Mm-hmm.
Yeah. Would that be your Fnet, or would it?
That would be your Fnet, because that's the only force in play. Well, okay, technically there's going to be a normal force, and there's going to be gravity. And sometimes we'd have to account for friction, but I'm going to say let's assume there's no friction, because that's going to make it a lot simpler. That means the only force is that restoring force. Pull it back this way. So what that means in this example is your restoring force is equal to your Fnet. So then your Kx is equal to your ma. So to get A by itself, divide by mass. So 54.9 newtons per meter is that leading coefficient value. The distance we moved this thing was 12 centimeters, so 0.12 meters. And then divide by the mass. Well, let's talk about the direction in a second. Let's do that. First, let's just find the value. And then we'll talk about whether we think it should be positive or negative. So just 26 then.
Yeah.
Okay, units for acceleration are meters per second squared. Now let's talk about direction. Which way is it accelerating? Yeah, it's accelerating backwards this way. So I need to have some sort of indicator that you know which way it's going. If you were just to say that it's going backwards, that'd be fine. If you were to like choose a direction as east or west and then make it go the other way, that's fine. If you were to denote this as positive and that as negative and say it's going towards the negative direction, that'd be fine. But you just got to somehow indicate which way it's going. Okay. My advice, ignore all that negative stuff because sometimes that gets confusing, and just use your logic when you're done and figure out, well, which way is it going? It's the same advice I gave you guys when we were doing kinematics. It's like sometimes 9.81 is positive, sometimes it's negative. Don't worry about the positive or negative until you're done. And then just figure out which way fits better. That makes sense? Okay. Okay, another formula I want to introduce to you is going to then relate a spring to the concept of period and frequency, which is our first topic. Let me try demonstrating this again, though, using my guy up there. Here, bring this closer. Thank you. Okay, so imagine that you've got your. You guys see that at all? Maybe. Okay, so imagine you've got this guy at a stationary position. Imagine I were to add just a little more force to it so I don't snap the elastic. Okay, do you guys see how it was going up and down? Okay, now this didn't do it particularly all that well. Like in a frictionless system, what should happen is just go up, down, and keep doing that repetitively for a long time. Okay. But this particular spring is not going to do that very well because I think one, this cord's getting in the way, and two, there is a decent amount of friction that's slowing it down. But does it make sense how this has like a periodic motion to it? You know, basically you can make it that wave by saying it's going back, forth, which is that up and down curve. So there's a formula for this that we can use then to figure out period, and it's based on this little camera here. It's based on 3 different variables. Okay. One of the things you need to know is the mass of the actual object that's being swung back and forth. And you also need to know that spring constant. And if you have that, you can solve for how long it takes for this thing to go up, down once, and then up, down again. Does that make sense? So it's really straightforward. It's just a basic formula. So my question here then is, let's try to calculate the period of the spring in that example we just did. So here's the information from that example. We had acceleration is what we were looking for, but now we've got mass, k, and distance. So the formula is period equals 2 pi square root of m over k. So 2 pi. Mass would have been the 0.250. The spring constant would have been that 54.9 newtons per meter. What number was irrelevant?
Why is like
I'm going to try to show you that in the simulator in the lab next day. That's probably the best way of putting it. But probably the best reason why is that if, I don't know that I can show this very well. Say this is your equilibrium point. If you pull it all the way out to here, it's going to have a lot of restoring force. It means it's going to accelerate quite quickly, and it's going to accelerate back and forth fast. Okay. which means that its period, even though it's got further distance to travel, its period will actually be the same as if I only pull it out to here. Here there won't be as much acceleration, and so it'll go slower back and forth. And the period will actually be the same for both. Give me a second, let me finish this here. I'll pull up the simulator we're going to use next week and I'll try to prove it to you. It's a very straightforward formula. I mean, you just plug in a couple of values and you're good to go. Anybody get an answer?
0.424.
Anybody else? 0.424?
Well, what the units?
Okay, so that goes back to our first lesson yesterday. T is period. Period is always measured in seconds. Yeah. So 0.424. So 0.42. Actually, I should be able to count all three. That 12 centimeters there, I didn't use that number. So that's how many seconds it should take for this spring to go there, back, and there. That's how long it would take. Does that make sense? Okay. Let me see if I can find that simulator we're going to do next day. Just bear with me for a second. Need to find the lab we're going to do. I don't know. I'm just going to teach till the bell goes and we'll finish the rest next day.
I feel like it's the same as like an assembly.
Yeah, I think it's what we had on Halloween.
Yes.
Will we ever have to like find what the second counts will be?
Ideally, we're going to work in a frictionless environment, and so it should always be the same. Like when I pulled that thing up and down, I know it kind of like it went here to there and it kind of shortened a little bit. But like ideally, it should always go like the same distance back and forth, and we're going to try to talk without friction.
Okay, so
Does that make sense? All right, did that answer your question, I guess?
well, I just it sounds real hard if I had to.
I think the answer I'm giving you is no. Okay, so here's the simulator we're going to use next week, Tuesday. Basically, what it's going to do is it's going to provide some springs hanging from the ceiling. And one of our goals is going to be to try to figure out how much the K value is on the springs based on how far the springs expand. So, for example, if I were to hang this 100-gram spring on here, okay, now when I do that, though, it's going to bounce up and down. So there's a way to, like, you have to turn friction on, I think is what has to happen. There we go. Now that friction's been turned on, you can then figure out how far in terms of distance the spring has actually been stretched. And then if we know that distance, and we know mass, and we know gravity, we can calculate the spring constant. That makes sense? But each spring might be different. If I were to take a 100-gram mass and put it on this guy, I was hoping the spring constant would be different. Need lots of friction. Okay, apparently they're the same. Spring 3, I believe you're allowed to change the hardness. Why don't I? There we go.
It's a hardness.
So like that would be the K value. So like you see how like this spring right here compared to this one's like a little bit like thicker. I think what they're meaning by this is that like the K constant for this one is more. So that, like they're both being attached by 100-gram springs, but this guy right here is like a tougher spring, if that makes sense. Anyways, for Carlin, for your question here, if I were to take these guys, let me just see that I can throw them there. Okay, I'm going to pause this thing. I'm going to pull this guy down to about, say, there. And I'm going to pull this guy down to here. I hope this works. When I unpause this and take friction all the way off, what should happen is this guy here, who's way further down, he's going to accelerate faster than this guy will. And what should happen is they should both reach this equilibrium point at the same time, I'm hoping. And then they'll go up and they'll come back down, but this guy's just going to travel a further distance. Let's see if this works. See how that works? So they both actually have the same period. They're both going up and down in the same amount of time. But what's happening is this guy just goes further, that's all. But the actual distance the spring traveled was irrelevant. If I wanted to figure out the period, what we do is this. We'll make the time go slower. We'll throw the stopwatch on. And so then I'm just going to pause. There. Okay. So now I will start the stopwatch. And then we're going to see how long it takes for this thing to go all the way back up. and then all the way back down to here. And that would be period. Does that make sense? So then I'll just do it at 1/16th time so we can watch it in slow motion. See how they both like start and stop at the same values? And so apparently that was 0.63 of a second. Does that make sense? So anyways, we're going to play around with this next week on Wednesday. So we'll come back to that. So, in terms of formula then, it's a very easy formula. You just need to know how to rearrange. It is possible though that I could ask you to solve for that k value. If I wanted you to solve for the k value, what would you need to know? We need to know period, which you could calculate by figuring out the length of time that it takes to go up and down like we just did, and then mass, which you could just weigh. So there's actually two different ways of calculating a k value. One is using this formula, and one is using the formula we used earlier where you make it equal to gravity. Does that make sense? Okay, let's start talking about pendulums. I might not finish this depending on how long I've got, but the second type of motion that involves like back and forth motion is a pendulum. Okay. Pendulums also have a restoring force. I found this example off the internet. Imagine that you pull a pendulum out to here. What is the pendulum going to want to do? Well, it's going to want to swing out here and then swing back and swing back. And so the typical example is this Keynesian or swing set basically, right? Friction does take place though, like friction usually slows you down slowly over time. So we're normally going to try to assume a frictionless environment. The reason why this force works then is that this part of a triangle down here is the restoring force. It's very similar to FD. Does that make sense at all? So like if you can see how this triangle is put in here, gravity is pulling you straight down. A perpendicular force exists right here. By the way, the perpendicular force is going to be equal to the tension in the wire. And then F restore is almost like the downward force that we did in the previous unit. So if you ever want to figure out how much force there is on a pendulum, it's actually just trigonometry. And whatever this angle is right here is whatever this angle is right here. That makes sense? So, couple things I need to point out here. There's actually three assumptions we have to have. First assumption is the angle that you pull this thing has to be relatively small. This does not work if you pull it all the way back to 90 degrees. Okay. So usually we want to talk about 20 or 30 degrees or less. Second thing, we have to assume friction does not matter. But I mean, obviously in the real world it does. If you're on a swing and you go back and forth, if you just sit there, I mean, you'll do this for a long time, but eventually you'll slow down and you'll stop. That makes sense? So obviously there are some friction forces in play, but they should essentially be very little. Last thing, we've got to assume the mass of the string is pretty irrelevant. When you look at my example there in the middle of the room, the string I used is like some sort of fishing wire. Does it have a mass? Well, yes. In comparison to the weight on the bottom though, is it very relevant? I'd say no. Like, I bet you the scale will hardly notice the mass of that string. So, here's a graph I found online. This is actually part of that sine curve that kind of does the whole back and forth, up and down thing. And what ends up happening is the force compared to the angle is more or less linear up until about here. So as long as the angle that you're using is about 30 degrees or less, these formulas work. As soon as you start making the angle like 90 degrees, it's not really a linear relationship because it's actually that wave back and forth motion. But like for at least the first little while, it's more or less linear. Here's an example. You've got a pendulum and you hold it back at a 10-degree angle. How much restoring force is there? So, draw a picture. Ceiling, pendulum. Pendulum is this long. I'm going to exaggerate this. This won't actually be 10 degrees, but imagine that I pull it back to here and that this is 10 degrees, even though that clearly is more than 10 degrees. What forces are in play on my pendulum? Well, for sure there's a gravity force, because that's pulling it down. We're going to ignore friction, though.
That would be good.
Well, gravity's going to try to pull this guy back down, but he's obviously not going to go back down for two reasons. One, there's going to be a perpendicular force, which should counteract the tension in the wire. Kind of like how this one's an upside down T and that one's a regular T. Nice symmetrical. What we're looking for, though, is the restoring force, which is going to cause this guy to start heading that way. And so normally it's been FD, but from now on, maybe we should call it FS back again. So if this guy is 10 degrees, and this guy is 2 kilograms times 9.81, it's honestly the exact same as our last unit, only rather than FD, it's FS. That's all. So, sine, cosine, or tan? Sine. Yeah. So it's sine of 10. And then you've got to multiply by FG to get what FS is equal to. So that'll be 2 times 9.81, whatever that is, times sine of 10. Units? Yeah, it's a force. Newtons. So that's how much force gravity is trying to pull this pendulum back this direction. That makes sense? What would happen if the pendulum were just sitting there? How much restoring force does the pendulum have as it just like lays there in the middle of the room? I'd say it has none, right? It's not moving, right? Well, here's a proof for that. At this particular point in the free body diagram, you've got gravity pulling down, you've got tension pulling back up. Do you have any restoring force going one way or the other? The answer is, well, no. Why would you? Does that make sense? So as this thing gets closer and closer and closer to the middle, the restoring force gets less because there's less reason for it to be pulled back. So the more restoring force would be the further out you go. Here's just another diagram of basically the same thing. Does that make sense though? You're looking for this bottom side of the triangle here. Okay, another example. Swings are great examples for pendulums. So Keynesian is on a swing, and the equilibrium position is 0.35 meters above the ground. You're going to want a diagram for this one. So top of swing, swing, so I can draw it like this here. Kinsey is swinging, swing thing there, and she starts off 35 centimeters above the ground. Oh, thank you. So 35 centimeters, but this guy should be meters. Thank you. My bad. Okay, well then I pull her backwards. So I'm going to then pull Keynesian back to here by a distance of 0.87 meters. So that now she's out, I'm going to exaggerate this a little bit, but now she is out here. I don't know that I can draw this very well. Thank you. I appreciate that. And so she's been pulled back here. Hey, Sean. Okay, one more thing. I'm going to tell you the length of the swing. And so the swing itself is 2.67 meters, which means that it's also from here to here 2.67 meters. I think I heard someone mention this. All this information here is so that we can try to find the angle. So that's our goal, try to find the angle. I'm just going to move one of these guys here. Move this distant. Oh, I can't pick just half of that up. Eraser. I'm just going to move this here. So this distance from here to here was that 0.87. How'd you find that angle? It's not tan.
What?
This angle right here, this guy's going to be opposite. This guy's going to be adjacent. This guy's going to be hypotenuse because of where the angle is.
Oh, 19
Oh,
degrees.
is that your mark?
Because I used sine.
You got to use sine. Yeah, you're going to have to do sine inverse of opposite, which will be the 0.87, over the hypotenuse, which will be the 2.67. You got 19 degrees, Rush?
Yeah.
Oh, it was like 1 degree off.
Well, it does make a difference in physics.
Yeah. I'm not stupid.
Not you.
Oh.
No, just stupid physics.
Yeah.
Oh,
Stupid. Stupid.
Ouch. Okay. Did that make sense so far for calculating the angle? So we can use trigonometry to find the angle. Now that we know that angle, okay, my first question was what was the height of the swing above the ground actually? So what I'm actually looking for is what is her initial height above the ground right now?
Wait, what?
Hmm.
How?
Okay.
You have to draw a second triangle.
You don't have to actually. What we want to do is figure out the distance from here to here.
So basically, you just use.
Find me the adjacent. Could you guys find me the adjacent in this triangle and find it from here to here?
Don't you already told you how?
Nope, because the 2.67 is down to here where she normally would have been. But when I pull her up to this distance right here, she gets a little bit higher when I draw this right angle triangle. So find me the adjacent from here to here.
I don't understand why this is. Because she's higher.
So she was this high off the ground. But as I pull this thing out here, it used to be this high, it's now this high. And so when I make my triangle, the triangle goes up to here, but normally it's down there. So what I'm going to try to do is find the adjacent up to there, and we'll subtract the difference.
So would you go like 2.67, subtract A, and then add on 0.35?
Yeah, that's kind of the concept here. You're going to have to calculate how far this distance is right here. I'll call it y. And then once you found what y is, you're going to have to add on that 0.35 meters to figure out her height above the ground. Because this distance here is going to be whatever y is plus that 0.35. So, first we got to find this adjacent side though, from here to here. Anybody find that? You could either use your angle or you could use Pythagoras' theorem.
I got 2.53.
2.53? Anybody else?
Yep.
Okay. Okay, so apparently this is 2.53 meters. You could either use like cosine or you could use Pythagoras' theorem. So then if this is 2.53, but down to here was 2.67, then y must be 0.14. Is that correct? Because 2.67 down to the base of where Kinsey's bum is on the bottom of the swing, but this distance right here is going to be minus that adjacent. And so then take your 0.14 and add your 0.35. So she's 0.49 meters above the ground. Does that make sense? Sorry, my work is very messy here. I hope you guys are able to follow that. Okay, we've already found the angle of the equilibrium point because that was 19 degrees. Last question was, what's the restoring force? So that would be as Kinsey is now 0.5 meters basically off the ground. Pardon me. What force is that downward restoring force? So if you want to, you may want to like redraw the triangle kind of in right here. Do this a little better. There to there to there. This would be gravity. This would be the perpendicular force. This would be the restoring force. This is that 19 degrees. Yeah, so we can find FG because I know Kinsey weighs 26 kilograms. So 26 kilograms times 9.81. And then it's always, just so you know, it's the sine of your angle. What was that? 450 pounds?
No, Carlin said this is like, isn't that like 50?
Well, it's like, it's
Yeah.
heavier than 1 kilogram, but it's lighter. I don't know, it's probably a good size for kids.
Is that what our belt probably?
Yeah.
Okay.
yeah.
Did you guys get an answer?
We're 83.
83?
Sure.
Anybody else?
Yeah.
83? Alright. We'll call it there. I'll pick this up again next week. But hopefully you can calculate 83 newtons. Alright. We've got an assembly, so our schedule is kind of compressed today. So we'll pick this up next day.